here are some symmetry elements. Here are all the symmetry elements actually that we will encounter in space group symmetry. And they can be classified. Crystallographers like to classify everything. Sometimes it's a little too much actually. But you can see we have some symmetry elements which we classify in two groups of symmetry elements. So the symmetry elements are here: rotation axis, rotary inversion axis, screw axis, glide reflections. They can be classified in different ways. We can say some of them are symmetry elements of the first kind, or proper symmetry elements, and some of them are called improper symmetry elements. And those that are improper are those that contains an inversion center. That means that if we have a molecule with a crystal and we impose this inversion on it, it actually becomes a new molecule, right? It comes to the other hand if we have a non-centrosymmetric system. So again, we can classify them in terms of elements that do not contain a translational component and those that do contain a translational component over here. So we have the rotation axis and the rotary inversion axis with no translational components, and then we have these other elements over here, screw axis and glide reflections. So you may notice that this is a little weird because we have rotation axis of one-fold, two-fold, three-fold, four-fold, and six-fold symmetry, but none of five-fold or seven-fold or eight-fold symmetry. Any idea why that is? Is that surprising? Little? Yes?
You have to be able to construct a plane out of, well, you can't do that out of pentagons?
Yeah, you can think of it like that, yes. So if you have pentagons, it's hard to construct a full plane, which is covering the whole plane. And the same goes for 3 dimensions, right? So, in fact, you can say there's a conflicts between the five-fold symmetry and the translational symmetry, right? So, the reason for not having this five-fold symmetry is that we do not have, or that we do impose this translational symmetry in the system. There's a class of crystals called quartz crystals, which can actually have five-fold symmetry, 10-fold symmetry, and that's because this translational symmetry is lost. But that's a little, you could say, it's a small subclass of crystals, so it's not so interesting for us today. Okay, let's go in and let's dig into these different types of symmetry elements and learn a little more about those. So, I guess the drawings here more or less tell you, if you didn't know already, what kind of elements this is. So inversion will basically make a full inversion of the whole object that we are inverting. And the mirror plane will, of course, create another mirror, right? So here we have a mirror plane in the middle here. And you can see how we describe these symmetry elements mathematically here. Then we have the rotation axis. So we have rotation of these sides here, right? 1, 2, 3, and 4 and 6-fold rotation. And the graphics is not so great here, but I have taken in these drawings here anyway because I'm going to use that a little more in a moment. I have a little exercise for you which involves these hands over here, so I thought it would be good to use them here. What you can see here is that if we have, for example, here a 2-fold rotation, we make a small illustration of the 2-fold symmetry axis here. It's supposed to look like a not a triangle, but a 2-angle. I don't know what you want to call it. It's a kind of ellipse or something like that, right? That's the element we have in here. And here we have a triangle down here to be able to say that it's a 3-fold symmetry axis. So the twofold axis in the plane here will then be just an arrow like this, right? So, yeah, okay, again I had this question down here which we have already addressed. Why don't we have 5, 7, and 8-fold symmetry in crystals? Then there are these elements called rotary inversion elements. That's a combination then of a rotation and an inversion. And yeah, you can basically see how it goes here. Here we have a 4-fold rotation and then an inversion, right? So we get these kind of elements. In this case here, whenever we have a inverted element, we get a shift of handedness, and we signify this also by making this white dot in the middle of the hand here. That's not, of course, very important for the general crystallography, but it's important for the exercises I have later on today. So, a one-fold axis with a center of inversion, basically, or with an inversion involved, is just an inversion axis. And this 2-bar axis, so we put a bar on top here, this rotary inversion, which is a 2-fold axis and an inversion, that's actually the same as a mirror plane. Right? So instead of writing 2-bar, we often write M. Mirror plane. Then we have these screw axes. And they are also very common in space groups and in crystallography in general. So they are written as this again this ellipse-like figure, but then with 2 tails on. And the same goes for the 3-fold. You have these small wings sticking out of the figure here, and they are used in general in crystallography. So all the space groups that we are going to talk about are listed in this giant piece of tedious work, crystallographic work. So in here we have basically all the 230 space groups. In fact, I think I got the wrong volume with me, so I have to bring for the next lecture. I'll bring the right one. It has to be number A here. So I can't show you the whole thing here. It's the same one. So this is actually the mathematical and physical tables, and there are many more of these books here. But I'll show you a picture of some of the pages in this volume A, where we have the symmetry elements in it. Then there is an element called a glide reflection, in Danish glideplan. And it involves then a reflection and a translation component. So you can see how it goes here. It's gliding along in the plane here, and then you have also a mirroring of that in the mesh, right? So we are gliding along here, and then we have a mirror. And there are different versions of those. There are those that are along the unit cell axis, but there are also some that are diagonal to the unit cell axis. So